Okay, so descriptive statistics. When you talk about descriptive statistics, we are just basically looking at a branch of statistics that help us to summarize our data into understandable formats. So we are going to be focusing on 3 types of descriptive statistics for our study, and that's a measure of central tendency, measure of variability, and measure of frequency distribution. I'll be elaborating what each of those ones mean, but that's basically what we are going to be looking at under descriptive statistics. So we are describing our data into a format that is understandable to the user or to the end person. You see, when you're given data, it's just rows and columns. Sometimes you just have a bunch of records, and it's up to you to make sense out of it. So in descriptive, we summarize that data to make it understandable for us. The first type that we are going to be looking at is what we call measure of central tendency. And here we just look at here we're just saying that this value attempts to describe the center of the data set. If you've been given a large data set or in data set, measure of central tendency gives us the center values of that data. Could be one value, could be a range of values. So that's what we look at under measure of central tendency. And in this, we look at 3 main should I call them fields or main terms? That's mean, median, and mode. I believe most of us are very familiar with what mean is. If you have any questions on that, feel free to type in the chat. But mean is just the average of your data. For example, if I gave you a data set and it had, let's use the example under median. I have that list of figures, 1, 2, 3, 5, 7. So mean is just the average of those figures. I get the summation of those figures and I divide by the number of my data set. So that gives me the mean. Then median is just looking at the middle value. In the next example I gave, I illustrated what median is. I showed you the list of maybe my data set, and the number in the middle becomes my median. Then mode is just the number that appears most. So I think we are very comfortable with those few terms. Because we are going to be using Python most of the time or in our biggest discussions, I thought it wise to give you some of the common functions that we use when we are talking about measure of central tendency. So we have a function in Python called mean, and that's the one we use for calculating the mean for our values. Then we have another one called median. And then for mode, we use another function called mode. I don't know if you've looked at functions in Python. I'm not so sure about that. But in case you haven't, I'm sure you'll be able to look at what functions are and how to write functions, how to use functions. This is just an example of how we use Python functions to carry out statistical operations. Any questions so far? Feel free to interject in case you have a question. I think there's a chat.
Yeah.
Okay. So I don't know what this one was answering. Yeah, functions?
He's saying that I've tried to cover functions before.
Oh, okay. So okay, that's nice. Okay. So another descriptive statistic term that we are going to look at is what we call measure of variability. And this one looks at how spread data is. For example, if you have two data points, let's say 1 and 2, we look at how data is, the difference between two data points. That's what we call the spread of data. So we have 2 points and we are looking at the difference between them. So in measure of variability, that's basically what we are looking at. With range, so under that we have 4 major terms that we use. We have range, which is just the difference between the maximum value and the minimum value, or the biggest value and the smallest value. Then we have variance. Who can give me an English description of what variance is? This is a mathematical definition of variance. Who can try to describe what variance is in English? Does anyone have an idea?
Maybe plus or minus, something like that, and recording those differences. Taking note of plus minus an average value, probably.
Variance is how spread the data is, how widespread the data is.
Okay. So I'm going to add something on your definition. I think let me first see the chat before someone could have answered it.
Someone here is saying that it shows how far the values are. Is it how different the values are?
Okay, so you're all partially correct. When you are looking at variance, we are basically looking at how far the value is from the mean. So variance and standard deviation, they both look at how far that value is from the mean. We've seen how we get the mean. The mean is our average of our data set. So we get each value and then we see how far is it from the mean. So that's what we call variance. Now we get the average of all that to get variance. So we are looking at, let's say if our mean was, what's the mean from this data set? 1, 2, 3, 5, 7. Who can do the quick math there? And you give us the mean.
Mean is 9. 9, I think, right?
We are going to take your answer. If you're saying 9, let's take 9. So with variance, we are looking at how far is 1 from 9. I doubt it can't be 9.
Mean is 3 point something, 3.2.
3 point what?
It is 3.6.
That is 18 divided.
Isn't
Yeah,
it?
18 divided by 5 is 3.4. Oh, yeah.
Please get your calculators and be sure. Because 9 is way out.
It is 3.6.
3.6.
3.6, yes. If our mean is 3.6 from this value from our data set, so we are looking at how far 1 is from 3.6, how far 2 is from 3.6, how 3 is from 3.6, how far 5 is from 3.6, like that. So that's what variance and standard deviation looks at. So the difference between the two is that for variance, we just take the average of those differences. Now for the standard deviation, we find the square root of variance. That's how different they are, but they both look at the same thing. So this is our mathematical function or formula for finding variance. X stands for each value here. For example, 1, 2, 3, 5, 6. Then mu is mean. Our mean, for example, in this example, our mean was 3.6. And then n is the number of items that we have here. Here we have 1, 2, 3, 4, 5. Yes. Now, I have an here. I said if we are using sample size, we use what we call n minus 1 instead of using n. In my formula here, I have n, but I said if you're using samples, we use n minus 1. So when you're dealing with data, we have what we call samples, like sampling. Sampling, you get a smaller size from the bigger population and you use it to carry out your statistical operations. Then, basing on the results, you make conclusions of maybe the bigger population. So if you have that kind of data, we don't take the n as the number of items in our sample size. The n we take is the number of items in our sample size minus 1. So what this would do, it will give us a bigger value compared to when we use just n. Am I making some sense there? Do you understand the concept of sample and population?
Mm-hmm. My people.
Yeah.
Could you just explain again one last time?
Could you repeat with some figures, for example?
Do you understand the concept of sample and population?
No. Could you repeat?
Yes.
Could you
I
repeat
need
once
a yes
more?
with an explanation. Okay, let me explain. When we are calculating variance, I've given the formula and it's this, yeah? I think we know what this one means. This one means the summation of everything. So we get the difference between 1 and 3.6, the difference between 2 and 3.6, 3 and 3.6. We add everything there. That's the summation we are seeing here. So my note here was about the n here. Now, when you're dealing with sample size, I said with sample size, you're getting a smaller group from the bigger population. For example, if you were told to collect data about women in Uganda, I doubt whether you can reach out to all women in Uganda. So what you would do, you would collect data from a sample of women in Uganda. For example, you can take a sample from each district, and then using that sample, you make your calculations and come up with conclusions. And then you can maybe say, because of this and this, because of my sample size, this and this, I've discovered that women in Uganda like eating matoke. Yeah, that's your conclusion from the sample, using the sample, because you couldn't find each and everyone in the population. That's what you call sample size. Now, if your data is a sample size, this n is not, don't use this n as your sample size. Yeah, the n you're going to use here, you're going to get the size of your sample minus 1. That's what you use here. If your data is just a sample, if it's not the full population, you use n minus 1 instead of n. Am I clear on that?
Yes, please. Thank you very much.
In the chat, they have understood.
And have we understood the concept of sample and population?
Yes.
Okay, so I just wanted that to be clear because you're going to find other formula where that's showing you that you're dividing by n minus 1. So I didn't want you to get confused by why are we using n, and then some books are showing us n minus 1. That's how it is.
Hello, madam.
Yes.
I had always wanted to ask this question. When dealing with the sample, why is it n minus 1?
Why is it n minus?
Minus 1? Yes.
Yes, why is it n minus 1? That one they subtract is to cater for like errors that could arise from your sample. It's a standard one.
Here.
This 4 gives us a smaller denominator compared to when we use 5, which gives us a bigger denominator. Now, when you have a division and the denominator is big, you get a small value. And when the denominator is small, you get a big value. So that's why I said it's better to overestimate than to underestimate. Remember, with samples, you're just dealing with estimations. You're not sure of what the value is exactly because you just have a representation of the population. So that's why we use n minus 1. Has it been answered?
I can also try to
Yes,
maybe.
madam. It has been answered.
I can also
Yes.
maybe try to add on
Joshua wants to. Yes.
that you see when we have the n minus 1 for the sample variance, it is because we want to get a better estimate of the true population variance, and some books call it Bezos correction. So now to maybe put it into perspective, let's say you took a sample of data from a large population, like measuring the weights of 5 people out of 1,000. So when you calculate the variance of your sample, you are using the sample mean, not the real population mean. And that sample mean is often closer to the sample data than the true population mean would be. So the variance will tend to be a bit too small and underestimated. Okay, so dividing just by n, it would underestimate the variance, but dividing by n minus 1 makes up for the fact that you used the sample mean, which is already fitted into the data. So that correction gives you an unbiased estimate of the population variance. So I think it now makes more sense. Thank you.
Thank you, Joshua. Clear now.
Okay. So another concept that we are going to talk about is what we call the interquartile range. Are we familiar with the word quartile? Or from just the English word, what do you think quartile is?
A quarter.
Is it like a quarter of something?
Yes, exactly. It's a quarter of something. So when we are dealing with data, we assume that our data is at 100%. So with interquartile range, we are looking at the middle 50 of that data. I tried to illustrate it in my next slide. So assuming we have 50 distribution, 100% distribution of our data. We have the first quarter, which is 25, the second, third, and fourth. I think we know that 100 divided by 4, which is the quarter, gives us 25. So that's why I'm having 4 25s. Now, when we get the middle 25s, we get the 50. And that is what we call the interquartile range. The difference here, the difference between this and this is what we call the interquartile range. In the definition, they said the range of the middle 50% of your data. So that's what I tried to illustrate here. Now here I try to bring in the numbers. Do you know how to find median when given such number? What's the first step when you've been given data, for example, like this, and you need to find the median?
You arrange your data in ascending order.
Yes. The first step is to always arrange it in ascending order. If you don't arrange it in ascending order, you're going to get misleading answers. So I arranged this in ascending order, and I first divided it by 2 into 2 parts to get my median. We say the median is the number in the middle. So this is my median number. This one, 12. Now I get the first half. I also divide it by 2. And then I also get the second half. I divide it by 2. Now, the median of the first half gives me what I call the first quartile. And the median of the second half gives me what I call the third quartile. So our first quartile is here. I think we know how to get median when you have 2 numbers in the middle. When you have 2 numbers in the middle, we add them, divide by 2. I did the same here. I did the same here. So my first quartile is 5.5. My second quartile is always the median. And then my third quartile is 16.5. So interquartile range just looks at the difference between the third quartile and the last and the first quartile. I think from this illustration you can see. In our definition, they told us it's the middle 50, that the range of the middle 50% of your data. So this is our range. This one here is our first quartile, and this one here is our third quartile. So that gives us the interquartile range. Any questions?
Excuse me, madam.
Yes.
What if our data is even? Let me say the data you are having there, we don't have. It's not odd, where we can have what? The second quarter is being for. What if it is even? How would you find the various interquartile ranges?
You follow the same stage. You see how we found assuming our data, like let's say it had another, I can add another 21 here. Yeah. So if I have another 21, it means my median would be between 12 and 14, right? Is that true?
Yes.
Yes.
So my median would be between 12 and 14, meaning that this one here will be my first half, and this one here will be my other half. Then when I get that other half, I also find the median. The trick here is to just find the median of your data. You first find the median of the general data. For example, here, of all the data, I find the median. Then after dividing your data into two halves, you continue to halve the halves that you've halved in the beginning. Does that make sense? So
Yeah.
just keep finding the median of your data set.
Yeah.
Thank you, madam.
Okay.
So, question: Does that
Yes.
mean that after finding the median, let's assume you found the Q3 and the Q1, the
Yes.
Q2 that has been, assuming from the last previous question, assuming that the numbers were odd. If I've got the median from this quarter one and the quarter three, then my interquartile is going to be the median, the number from maybe the median of quarter one and the median of quarter three, and then that would be my interquartile range, right?
Yes. For example, if we took, now if we add another digit here, I think our first half will be up to here, right? And that will mean that our median would be 6. Isn't that true? So if our median, this side is 6, so our quartile value 1 is going to be 6. And this side, I think it's going to be 16. Yeah, so that's how you find it. You just need to know how to find median, and you keep dividing. You first divide it into the first half for the median, and then you divide the two halves to get their median. So that's interquartile range. Very simple. But this is when they've given you such data. It's not going to be the same. So assuming you have 1,000 data that is like 1,000 figures, you can't keep dividing and dividing. It's hectic. So in Python, we use a function called percentile. So percentile, this 75 is our third quartile, because I think you all agree that at this point we are at 75%. Then at this point we are at 25%. So our third quartile is our 75th percentile, and then our first quartile is at 25th percentile. So we have those functions in Python. We don't have to worry about dividing big data. Let me see if there's a question here.
No, I'm just telling them that
Is that
these functions come from NumPy, and they shouldn't be worried that they haven't seen such functions yet. We shall see NumPy after pandas, but I wanted you to have a look at how these functions look like beforehand. So they come from NumPy. When you see the np.std, that is all. Those are NumPy functions.
Okay. Someone had a question?
no, that's what I wanted to ask. The NP, I was asking if it stands for NumPy.
Yes, NP stands for NumPy. Do you know what NumPy is? I think NumPy is it a library, Joshua?
Yes, it is a library, just like pandas. They have already seen pandas, so it is also a Python library for numerical Python. That's what NumPy stands for. So we shall see it next after completing our pandas, but it's a library.
Okay. So the last concept under descriptive statistic, measure, yes, under descriptive statistic, the last type is what we call measure of frequency distribution. And here we are looking at how often the value occurs in a data set. So the key terms that we look at in this category is plotting a histogram. Basically, we look at the visualization of our data through the histogram, box plots, and pie charts. Do we know what a histogram is? Have you ever seen a histogram?
Yes, we
You want
do.
to
They
show
are
you?
bars, just like bar charts. Though they
Yes,
are
we do.
reproducing from the bar chart.
What's the difference between a histogram and a bar chart? Visually, like when you look at them, because they look similar, but there's a difference.
A histogram has no spaces. A bar chart normally has spaces between
Yeah.
That's clear enough.
And he's correct.
We can take that. We can take that visually, yes.
A histogram is like more of like a bar graph, and a pie chart is like maybe a circle with partitioned parameters, whether in percentage or numbers.
This one is saying.
I was asking the difference between a histogram and a bar graph because someone said they look alike, but they are different. And someone told us that the difference between them is the space between the bars.
Yeah.
Also, I think we can look at how they are plotted. With a histogram, we use frequencies. Then with a bar graph, we use the actual values instead of their frequencies. Okay, so box plots. I was supposed to show you how a box plot looks like. That's your homework. Do we know how to use Excel? It's the basic statistic tool that we all need to know before we even go into pandas and NumPy. We should at least be comfortable with Excel. So with Excel, we can plot a box plot. So a box plot shows the distribution of your values. Usually we use it when we are identifying outliers. Outliers, these are extreme values from the rest of the values. For example, if I collected data and most of the data is between 1 to 10, and then I have a random 100, so 100 becomes my outlier. So usually box plots help us to identify those values that are far different from the rest of the values. We use box plots a lot when determining outliers. And then we know what pie charts are. Just a circle with slices corresponding to categorical shares of that data.
Question.
Yes.
Outliers. You're saying they are what? Do you mean like that data that is not corresponding with? Okay, for example, if I have ages of 20 to 25, and then I have someone who is like 60. Is that what you mean? Like that outlier, that data that is not corresponding with what we have?
Yes. Though that example of age, I just brought it to illustrate It's not necessarily that when someone's age is different from the rest is an outlier, but we are looking at data, assuming you've collected data, and then there is a figure that is so different from the rest. That's what we call an outlier. I gave an example of age, the same example you've also given. If you've collected your data and all the people you've interviewed are between 10 and 24, and then you have this gentleman that is 100 years. First of all, was he your target? Was that questionnaire a good representation of him? Something like that. So because of the big difference between his age and the rest of the data, his age becomes an outlier. So an outlier is that value that is very distinct from the rest. For example, you've been collecting data and your data is just text. You've been collecting, asking people questions, yes, no questions, and someone just puts a figure. So that figure becomes an outlier. As long as it is different from the rest of the data, it's what we call an outlier.
Outlier.
Okay.
Yeah. So these, I gave some examples. I think since you've already covered functions, you'll be able to do some of these things. I just gave some code example of how we can plot the histogram, the box plot, the pie chart, and all that. I'll be sharing this content after our discussion, maybe, and you can go through and practice. Okay, any question about what was that? About descriptive statistic before we go to another concept.
I think we can go to another concept.
Okay. Okay, so another concept we are going to look at today is what we call random variables and probability distributions. So we know what a variable is, right? Do we know what a variable is in Python? What's a variable? If I have x is equal to 2, what's my variable there? If I have an expression, yes, x.
Your variable is x itself.
Okay, good. So when we are looking at random variables, we are looking at the values of the numerical value, a numerical quantity whose value depends on the outcome of an experiment. For example, I said if I have an expression x is equal to 2, x is my variable and the value is 2. So with random variable, we are looking at x whose values are determined from the experiment. We don't know the value of 2. We don't know the value of x until we carry out an experiment. That's what we call a random variable. So x can be 2, x can be 10, x can be 15, x can be any number from our experiment. That's what we call a random variable. We have two types of random variables. We have what we call discrete random variables, and these are countable integers. And then we have what we call continuous. So continuous random variables don't have like distinct, you don't have a single digit to represent your value. It's rather a range. You have, let's say, from this range, from this value to this value. That's what you call continuous. So when you're assigning this x, your values are in a range. They are not like x is equal to 1. Now, when you have something like x is equal to 1, x is equal to 2, that's a discrete random variable. So that's what random variables mean. That's just the overview. And I've given you an example of what a random variable is and what a discrete, what a continuous random variable is. I have here like generic examples of random variables. I'm flipping a coin. That's for discrete. So when you're flipping a coin, you expect two answers. I mean, yes, you expect a figure. Yeah. For example, I said number of heads in 3 coin flips. So each time you flip a coin, how many times do you get the head? That's an example of a discrete random variable. So you don't know how many times you're going to get the head. That makes it random. But because you know it, the possible answers are either 1, 2, 0, 1, 2, or 3, because you're taking 3 chances. So that makes it the discrete. Now, when it is continuous, you just have a range of values that can be assigned to x. Am I clear on that?
Yes, please.
Yes, you are.
Okay. Yeah, and that's then another type of or another concept that we are going to look at is what we call probability distribution. Now, probability distribution looks at how probabilities are distributed over values of a random variable. So you have this random variable, and you're looking at the chances of getting that value of the random variable. For example, in our flipping the coin, we had these values 0, 1, 2, 3, 0, 1, 2, 3. So what are the chances of me getting 0? What are the chances of me getting 1? What are the chances of me getting 2? What are the chances of me getting 3? So that's what probability distribution is all about. And in here, we have types. We have what we call discrete probability distribution. So, and this one is used for discrete random variables. So we've looked at what random variables are. I mean, we've looked at what discrete random variables are, and now we are looking at discrete probability distribution. So what is the probability of getting those discrete random variables? And the common examples here are what we call the Bernoulli distribution. So with the Bernoulli distribution, we expect 2 outcomes per trial. So what I mean by per trial is every time you play this game, or every time let's say you flip a coin, that's 1 trial. So you expect either the head or the tail. So if your bet was on the head and I flip the coin and it shows the head, that would be a success. If it shows that the tail, it will be a failure. So with Bernoulli distribution, you only have two possible outcomes, either success or a failure. Now we have another one we call the binomial distribution. So the binomial distribution looks at how many successes are you going to get per independent trial. For example, if you're flipping the coin 5 times, how many times are you going to get a head? If your bet was on the head, meaning your success was on the head, how many times are you going to get the head in 5 trials, in 5 flips? So that's what we call the binomial distribution. Then the last concept or the last example under discrete probability distribution is what we call the Poisson distribution. So this one looks at the number of events occurring in a fixed interval. For example, how many times are we getting the head in 5 flips in an hour, something like that. So you have every after an hour, you flip the coin 5 times, you see how many times you get the head. Every after an hour, you flip the coin 5 times, you see how many times you get the head. So that's what we call the part. It's called Poisson distribution. Any question on that? Now this one has examples, and I'm going to need you to carry out some calculations. So make sure you've understood. Are we good? I don't like the silence.
Yes, please, kindly continue.
Okay. So with the Bernoulli distribution, we've said there are only 2 possible outcomes. So the total probability of any outcome is 1. Yeah. Now, if we are saying that suppose a rapid COVID test has 90% chance of correctly detecting the virus, that means our probability is going to be 0.9, because we are saying that the total probability is 1. So if our success is if our success is a 90%, that means it's a 0.9. We get what's 90% in what's 90% in decimal representation, I think. Should I ask it like that?
Yeah, it's 0.9.
9.
Yes, 0.9. Yeah. So the probability of this test not working, what's the probability of this test not working?
0.1.
0.1.
Yes, 0.1. So that's just what Bernoulli distribution is all about. Now, binomial distribution, I think I have a formula for all these. Let me first see. Yeah. So binomial distribution, this is the mathematical formula for getting the binomial distribution mathematically, but we are not going to be doing this. We are going to be using Python functions. Another reason to appreciate Python libraries. So instead of us cramming this whole function and whatever it means, we are going to just use Python. So, but for our study purposes, it's best that we know what this means. Yeah. So this is our formula. We are looking at probabilities. I want you to remember that. So we are looking at the probability of x is equal to k. So when I say x is equal to k, I'm just saying the probability of maybe success, the probability of maybe failure, depends on what the question is asking. So K is the number of successful events, N is the number of trials, P is the probability of success on a single trial, and then 1 minus P is the probability of failure. I think we have that. Now this N then K, this expression here, this is how you can express it mathematically for a simpler evaluation, because I doubt that some of us can pull off this. If you can, using a calculator, well and good. If you can make it simpler, this whole line is just NK. I think it's like a matrix expression. This is how this is the detailed description of NK here. It's N. What does this symbol mean?
Factorial. Factorial.
Yes, it's N factorial divided by into K factorial times N minus K, everything factorial. So this one is the NK here. Then this can easily be gotten as long as you know what P means, you know what K means, you know what N means. And then the formula for the Poisson distribution is like this. And this is what each of those values mean. Lambda is the average rate of events occurring, also known as the mean. So then the E is the base natural algorithm. I think, are we familiar with this natural algorithm symbol E? If we are not, this is a standard. Then we have pi, then we have, it's a constant. And then we have K, which is the number of events. So that's what this formula stands for here. And these are some of the examples I came up with to help us understand or to help us calculate the binomial distributions and the Poisson distribution. So you're going to go through these examples, and you're going to use this formulae, this for binomial and for Poisson, to calculate the respective distributions. So for this one, we are asking for what is the probability that 7 of them develop immunity. So we have here a scenario. They're saying a vaccine is 70% effective. If 10 people receive the vaccine, what is the probability that 7 of them develop immunity? That's our question. And using the binomial distribution, we are able to find that probability. I did this using Python and I came up with this answer, but I want you to use this mathematical expression to see if we shall come back with we shall come to the same answer. You can do it as practice. I don't think that I can wait for your answers. But I hope we are following.
Yes, please.
Okay, so that was the discrete probability distribution. Let me first confirm, what time does your class usually end?
It is
9:30.
9:30. Okay, so we have less than 30 minutes. So another concept that we are, or another type of probability distribution is what we call continuous. Remember the first one we looked at was for discrete variables. Now we also have the continuous variables. So for finding the probability of continuous variables, we also have what we call a continuous probability distribution. So here we use what we call the normal distribution, uniform distribution, and the exponential distribution. I have two graphs in my next slide. I need someone to tell me, first of all, what's the difference between A and B. Don't mind the height. Leaving alone the height, that one, it was intentional. Okay, it wasn't intentional, but it's not the difference I'm looking for. Who can tell me the difference between A and B?
Let me give it a try. A is evenly distributed, while B is distributing away from the what? From the mean.
Okay, that's him. Who else has not something? Yes, Matthew. Matthew, I see you right.
The difference, I'm not matter, but the difference between A and B, A is normal, since each side is equal. Then B is skewed to the left, right? It is skewed to the left.
Okay, yes.
Skewed to
So
the right,
when you are looking, okay, that's perfect. Those are very good observations, and yes, you're very correct, both of you. So when we talk about normal distribution, we are looking at the probability density against the values of that data set. And when we say normal distribution, what normal distribution means, there is uneven distribution between on the two sides of our curve. So if this is our mean, this side and this side is the same. That's what we call a normal distribution curve. This one is a skewed curve. I don't know. I think this is right. It is skewed to the right. So this one is not a normal distribution curve. But this first one, I think I tried to represent it well. It's a normal distribution curve. So that's the major difference between the two. And it's not like you're going to have your data in a curve, but sometimes when you visually, when you describe when you come up with these visual representations for your data, you're able to see which one is normally distributed, which one is not normally distributed. So that's what normal distribution is all about. Who knows how we plot a normal distribution curve in mathematics? How do we get to a normal distribution curve?
I think the scatter plot. Scatter graph, scatter plot.
Scatter. I don't think that a scatter plot can give us a normal distribution. First of all, what we need to know is that this curve is gotten. Yes, histogram. This curve is gotten by joining points. Yeah. It's not. So there is a point here. 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 There's something like that. Yeah. So in mathematics, usually we draw a histogram and then we join the mean, the median of each bar to come up with something like this. I don't know if anyone has a better explanation of how they get a normal distribution graph.
Yeah, that's how you do it. You get the X and Y values where they meet, you put a point, and you do that for the rest of the values. And then after getting all the points on the graph, you connect them, which creates that curve. That's how you do it, the way you've said.
Okay, so in continuous probability distribution, we look at a normal distribution which follows the normal distribution curve. Then we look at uniform distribution. Now, with uniform distribution, the difference between normal distribution and uniform is that for uniform distribution, we expect that all the outcomes are the same. We expect that all the probabilities of that occurrence happening is the same throughout. So I'm going to share some of these resources for better understanding, because I know 1.5 hours not technical enough for us to digest everything. So that's why some of these slides are just one slide, others are detailed. Yeah. Okay, so this is just a visual representation of what a uniform distribution curve looks like. I used curves to illustrate, but you're going to have data that is uniformly distributed, and you need to carry out some calculations to identify that this data is uniformly distributed. But this is how it is visually. And then for the exponential distribution graph also is skewed. I think this one is skewed to the right. I didn't complete it fully, but yeah, it is skewed. It looks like that. That's the exponential distribution curve. So here we look at the time between the events that are continuous. So this X is continuous, and then we look at the difference between the time in the distribution. So that's what exponential distribution looks like. I had said we are only going to look at 2 concepts, but I think we still have some few minutes. I want to skip this slide because if I explain it in these few minutes, it will not be beneficial to us. So I'm going to skip it for today's class, and in the next class I will explain it in detail, because it doesn't have enough content for me to explain. But I'm going to explain what we call hypothesis testing. Before I go to hypothesis testing, any questions so far?
I think so far so good.
Okay, so who understands hypothesis? I have the definition there, but just in your own understanding. What is an hypothesis?
I think it is theory under testing.
It's a what?
Theory under testing to be proved.
Yes. A theory under testing. Okay. Anyone with a different idea?
I think it would be an educated guess about a relationship between two or more things. Like, for example, if I said that people who exercise regularly have a lower blood pressure than those who don't. So it's just a testable statement or an educated guess between about a relationship between two or more things.
Okay, so we have two answers. We have a guess and a theory. So both can be correct depending on how you understand them.
Good.
But one thing that is very common in the two definitions is that both of them are subject to testing. We are not sure, or we are not concluding with whatever it is. If it's a theory, it's not yet tested. We are just assuming. So I like to call hypotheses as assumptions, things that you make up, you assume, and like assumptions, guesses, theories. So as long as it can be subjected to testing, you call it hypothesis. And hypothesis, is it hypothesis? Okay, we shall understand that. So hypothesis testing is a formal process that is used by statisticians to determine whether a claim is true or false, and it's supported by data. So the keyword here is it has to be supported by data. If you're claiming that exercising increases blood circulation, blah, 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 can you prove that? So that's what we call hypothesis testing. So you come up with a theory, you come up with a claim, you come up with an assumption, you come up with a guess, and using the data, you draw a conclusion whether your guess is true or false. So that's hypothesis testing. Now, in hypothesis testing, we have what we call the null hypothesis, or what I like to call the H-naught. Now, the null hypothesis is the default hypothesis, or this is what we call an innocent until proven guilty kind of statement. So it has no effect on our conclusion, something like that. So that's what we call the null hypothesis, or what we call the H-naught. Then we have what we call the alternative hypothesis. So the alternative hypothesis is the claim that we want to prove or we want to find evidence for. For example, in the explanation Joshua gave us was exercising. I don't remember exactly what it was. He said exercising, I'm just going to use my own. Exercising increases blood circulation. I don't know how you can measure blood circulation, but assuming that was my claim, that exercising maybe for 30 minutes a day increases your blood circulation by 20%. So that's my claim. So what I want to test is if exercising actually increases blood circulation. So that will be my alternative hypothesis. Whatever I want to find evidence for is what I call an alternative hypothesis, or H1. So that's what hypothesis testing is all about. And that's what H1 means, and H2, H0 means, and H1. So with hypothesis testing, we are just looking at H0 versus H1. We want to know, are we taking the H0 or are we rejecting it? So it's all about rejecting and accepting the null hypothesis. Another thing to note about hypothesis testing is that they are mutual, H0 and H1 are mutually exclusive, meaning that if you reject one, you have to take the other. You can't reject both and you can't take both. So we are going to look at some examples of some claims, and we see what H1 is and what H0 is. When you're doing hypothesis testing, you follow these steps. Step 1 is to define your H0 and H1. I say that H0 is that null hypothesis or the no effect hypothesis, or that what we are going to assume is true at that point. Then H1 is what we are trying to prove whether is true or wrong, or what we are trying to find evidence for. That's H1. Then we have what we call the confidence level. This sign here is representing the confidence level. So significance level, sorry. So the next step is to choose the significance level. The significance level is just the probability of you rejecting the null hypothesis when it is correct. For example, when you're carrying out hypothesis testing, you're trying to make sure that you find evidence to either support H1 or H0. So what if your null hypothesis was right, but you ended up rejecting it? The percentage that you want, okay, let me say that the percentage of you being wrong when you actually, the percentage of you being wrong is what we call the level of significance, the significance level here. So we always take 5%. You want to be at least 5% wrong, because when we are making this testing, we don't assume that you're going to be 100% correct. So at least you be 5% wrong. Don't go beyond that. We use 5%, we use 1%, we use 10%. Those are the commonly used percentages for significance level. And then the next step is what we call selecting a test statistics. We have like 4 test statistics that we can use. We have what we call a t-test, a z-test. We have what we call a chi-square. And yes, those are the commonly used statistics. We use a t-test when our sample size is less than 30. We use a z-test when our sample size is more than 30. Then we capture the p-value. The p-value is just the probability value of our test, of our t-test. And then you compare the p-value and the significance level. We are going to look at all these things in details. Don't worry, there are so many new terms here. That's if they are actually new, I'm assuming. Yeah, but for today's class, we are only going to look at identifying H0 and H1. And this is where I want you to be attentive or to help. So this is my first claim. A company has developed a new fertilizer and claims it increases the average crop yield for corn to more than 150 bushels per acre. A farmer wants to test this claim on his land. Mm-hmm. So what's our H1 and H0? Mm-hmm.
I think H1 is the 150. No. 150, right?
150.
I'm not sure.
Okay. So when you're writing this, step one, we have to represent this in, we need to represent it mathematically. So we are going to transform this text from the text to a mathematical expression. So that's step one. I think let me give you this as an example. So our claim is a farmer wants to test this claim. What is the claim? The claim is that the fertilizer increases crop yield to more than 150. Yeah. So if my crop yield, if I represent my crop yield by Y, so my claim is Y is greater than 150, right?
Yes.
Yes.
Yeah.
Yes.
That's the claim. Yeah. So Y greater than 150 is the claim. That's how you represent a claim mathematically. Now, how to identify H1 and H0 usually comes with the question that is following. We said H1 is the claim that we want to find evidence for. So what are they finding evidence for? They are finding evidence for whether the fertilizer increases crop yield to more than 150. So Y greater than 150 becomes our H1. Is that making some sense?
Yeah.
We shall get there. So Y greater than 150 becomes our H1. Another trick. I said H1 and H0 are mutually exclusive. Also, H1 and H0 are the opposite of the other. So mathematically, if you have Y greater than 150 as your H1, your H0 is going to be the opposite of that. What's the opposite of Y greater than 150?
Less than 150.
Less than. Is that less than? What's the opposite of greater mathematically?
Why less than 150?
Pardon?
Why less than 150?
Less than 150. Okay, another answer?
Can it be 150 less than the Y? Can it be like a full-fledged reverse?
It's Y less or equal to 150. Do we know that?
Okay.
Like in mathematics, when you have a greater sign, the opposite of greater sign is less or equal. Yeah? That's the mathematical rule. When you have a greater or equal, what would be the opposite?
Less or equal.
Less than. Yeah. So that's another note to take. That's another trick when you're interpreting these claims. First of all, express the claim mathematically. 2, use the subsequent question to identify H1 and H0. Usually H1 is easy to identify because it's the question. So when you find H1, just take the opposite of H1 and it will be your H0. That's the trick of identifying H1 and H0. Our time is up. I don't know if you still, but this was our last discussion. I have 3 examples. You can work them out and share your findings. I don't know if you have a a platform where you share your answers. I'm not so sure yet, but you can just practice and you see how easy you identify this H1 and H0. When we meet again, we should testing, and we look at linear regression. Then we shall also look at expectation and variance. If you have a question for me, you can ask. Otherwise, have a lovely evening.
I don't know if we have any question from the class. I think we don't. So I would love to, of course, take this opportunity to thank you for being explicit. Yes, Douglas, you have a question?
Sorry for interjecting. I'm just trying to get clarity. You said H1 and H0 are exclusively?
They're mutually exclusive.
Mutually.
So one can't exist while the other exists.
Yes. They don't exist together. It's either H0 or it's H1.
Okay. Thank you.
So yeah, so I wanted to thank Josephine for being explicit in this tutorial, and I believe that my members have really understood what's going on, and I know most of you have questions, are wondering why learn statistics when we are dealing with machine learning and AI. So of course it's basically because statistics is the foundation of machine learning and AI, and it just basically helps you to understand and evaluate and improve intelligent systems. Because as we say that machine learning starts with data, and statistics helps you summarize that data, helps you explore it, helps you clean it, and you'll use things like mean, median, variance, all those that I've been looking at to know your data before you actually train models. And of course, you want to make predictions, and most of these predictions of these models are based on probability and statistical reasoning. So for example, you can train a classification model which may maybe predict a 70% chance of a patient having diabetes, and then you can that is already statistics